And that means that my unrestricted wave function here is actually a combination which was supposed to be a singlet, but that's a combination of well, actually in this case mineral base set H2, that was the restricted Hartree-Fock singlet plus the double excited singlet in the dissociation limit. That brings the ionic, plus unfortunately part of a triplet wave function. And that means that this is not an eigenfunction of S squared any longer. S squared. That's sort of for the dissociation limit. So this is called spin contamination. You have distributions of higher spin included in that unrestricted Hartree-Fock calculation. That's sort of the price you pay for getting this correlation in, although you have a single determinant wave function. And in the simple example here, it's just a triplet. In general, it would be also quintet, heptet, and so forth. It would have higher spin states included. If you try to do a radical, which is a doublet, you would have contribution from quartet, sextet, octet spin. So instead of having S equal to 0, you have also S equal to 1, S equal to 2, S equal to 3. If you go for an S equal to 1/2, a doublet, you would have S equal to 3/2, 5/2, and so forth. So it's always one S value higher you would have included there. So in the dissociation limit, you get the correct covalent terms, which means you have correlation included, but you don't get the proper spin anymore. Now, if you're somewhere in between the equilibrium geometry and the dissociation limit, you sort of have a mixture. You still have a bit of correlation also included, but you also have the spin contamination included. And they sort of work against each other. The correlation gives you a lower energy, the spin contamination, because you have excited states included there, excited states with a different spin symmetry, will rather give you higher energies. So you still probably get something lower than restricted Hartree-Fock, but not as low as it would be if it only correlation. And in places like transition states, you don't really know where you are. So spin contamination is not good. But you can check that. So if you do, and that's really important for DFT calculations. It's more a problem actually for DFT calculations. But so you have to check, if you do a calculation of radicals, unrestricted DFT calculation with radicals, you have to check whether you have that, or how much of you have. So you better check what the program tells you, what the expectation value of the S squared operator is. And most programs print that somewhere. And you know, that should be S times S plus 1. If it's that, then this is a pure spin function. So for S equals 1/2, a doublet, and one unpaired electron, that should be 0.75. For a triplet, S equals to 1, that it should be 2. And sort of the rule of thumb is, if you get And I mean, all this spin contamination is going to make the value larger, because you have contributions of higher spin functions. Function with a higher value of S. So you will get a larger value in your output if you have spin contamination. If it's 10% off, that's okay. That's not a lot of that. If it's more than 10% off, you've got a problem. There are two ways, or three things you can do about it. If you're doing correlated wave function calculations like metal-plastic perturbation theory, which we're going to talk about next week, there's an unrestricted metal-plastic perturbation theory based on unrestricted Hartree-Fock wave functions. There's actually a way to project the higher spin symmetry wave functions out. That's then the projected metal-plastic. There you can do that. The problem is that works for the energy, so you can get an energy with the original unrestricted and one where you have projected the higher spin functions out. That works for the energy, so the energies are fine, but that's not part of the geometry optimization. At least as far as I know, that is not done for the gradient. So when you optimize your geometry, you optimize it with the spin contamination. Only with the final energy which you calculate then, you can project it out. So if you have a problem with spin contamination in wave function calculations, go for an MCSDF, because there you control it. You just include the determinants which you need, which have the proper spin. If you're doing DFT, and you can see that you get a large spin contamination, well, there are thousands of DFT functions out there. Just choose another one and see whether it goes away. Hopefully that functional then still is good enough for what you're trying to do, but there's no other way you can do there. Find another functional. And sometimes even there you are forced to say, okay, this is something for an MCSDF calculation. There's too much spin contamination, I can't control that.